So let's look at a power series as both a linear and a quadratic approximation. Keep in mind, to evaluate polynomials, we simply substitute a value for x, and then we use addition, subtraction, multiplication to find the exact value. Now, when we're dealing with approximating transcendental functions such as sine of x, or possibly like something like e to the x, or algebraic functions like square root of x, it's not a simple matter of addition, subtraction, and multiplication. These are a little bit more complex. So what we can do is use linear, quadratic, and higher order approximations to approximate these values. Now just quickly, let's do a quick review of linear approximations just so that we're all up to speed on this idea. Let's start off with some curve that perhaps looks like this, and we have some known value a, and we know what f of a is. So I know a and f of a. So I know this point. I know these coordinates. Now for linear approximation, what I'm going to do is simply find the equation of the line tangent. So once I do that, I know I have a point, and that point is a, f of a. These are actually numbers now. I know what they really are. If I take f prime of a, that's going to give me the slope. So I can use y minus y1 equals the slope times x minus x1. And then I'll have, well, keep in mind actually that y1 and x1 is this known point. So I'm going to substitute that for f of a, and the slope is f prime of a. So that gives me y equals f of a plus f prime of a times x minus a. That's going to be the linear approximation based on this known point, a f of a. That's what gives me the slope of this tangent line. So with that in mind, let's do a linear approximation, then a quadratic approximation for f of x equals sine x near x equals pi over 6. So let's just draw a quick picture of this. Sine of x will go like that, and basically it's a picture that I just drew. Oops, I don't want a there. Actually, I want pi over 6. So I know my point. My point is going to have coordinates pi over 6 and sine of pi over 6, which is, of course, pi over 6 and 1/2. So that's the coordinates for that point right there. Now, the first derivative, f prime of x, is equal to cosine of x. And I want to evaluate that at x equals pi over 6. That's root 3 over 2. So that's the first derivative at a, so to speak, because a is pi over 6. So that gives me my linear approximation. So y is going to equal f of pi over 6, which is 1/2, plus the slope, root 3 over 2, times x minus a, which is pi over 6. That's the equation of the line tangent at pi over 6. So if we switch to Maple real quick, we can see here's sine of x, and the red line is our linear approximation, which it looks pretty good. Now notice if I take the first derivative here, y prime will equal root 3 over 2, which is the same as f prime of pi over 6. So my original function and my linear approximation, first derivatives both match. They're both root 3 over 2. So I've successfully matched the slope at this point. Now for the quadratic approximation, what I'm going to want to do is add more detail. So if I use a quadratic, a quadratic function, your basic x squared looks like that. It's curved. So I should be able to come up with a quadratic that matches concavity, that has some curvature like this, that would give me an even better approximation for values of x near pi over 6. Now clearly with this linear approximation, as I get farther and farther away, my estimations get worse and worse and worse. So let's take a look at the second derivative, f double prime of x. That's the derivative of cosine, which is a negative sine x, and I will evaluate this at pi over 6. That's a negative 1/2. So what that gives me for a quadratic approximation then is y equals 1/2 plus root 3 over 2 x minus pi over 6. There's my linear approximation. I'm going to add to it the quadratic term, which will be negative 1/2 times x minus pi over 6 squared. And sure enough, this is a negative quadratic, so I'm going to have concavity that should look something like that. Now, what happens if I take the second derivative of this? Well, the first derivative will be root 3 over 2 minus 2 times 1/2 x minus pi over 6. So that would then imply that the second derivative is going to be negative 2 times 1/2. But that's not equal to the second derivative of sine. It's multiplied by 2. So I can correct this simply by dividing by 2. So I'm going to come back up to my original approximation here, take this whole thing and divide it by 2. Now when I take the second derivative, the 2's would cancel out, and then I'm going to have the second derivative of, let me see here, y double prime will then equal 1/2, a negative 1/2, which would be equal to f double prime of pi over 6. So our approximation now looks like y equals 1/2 plus root 3 over 2 times x minus pi over 6 minus 1/2 x minus pi over 6 squared divided by 2. So let's go ahead and take a look at Maple and see how good that looks. Now I went ahead and put it into Maple, only I did not divide it by 2. This is what it looks like when I did not divide by 2. And you can see that this curve, this kind of beigeish, yellowish thing, is closer to sine of x than the linear approximation. It actually does do a better job. But when I divide this by 2, which is my actual approximation, now see what happens. Near pi over 6, this really matches very, very well. Extremely well. But I'm going to go ahead and, let's see, I'm going to take my domain, I'm going to change my domain, and, well, let's just go up to pi. That should be plenty to get a good idea. You can see very near pi over 6, this really does a nice job here. But what's going on is beyond that, it's not doing a very good job. And I think what I need to do is I need to increase my y a little bit so you can get a better look at it. There we go. And actually I have my colors turned around. No, I didn't. This is sine x, and this is the, this is sine x, and this is the approximation. I did get my colors turned around when I was looking at it a little bit earlier. Okay, so just for the heck of it, let's do one more. Let's do a third order approximation. So what I'm going to need is f triple prime. Now if we go back, f double prime, the second derivative was negative sine x. So what I need is the derivative of negative sine x, which is going to be negative cosine of x, and I want to evaluate that at pi over 6, and that's going to give me a negative root 3 over 2. So my third order would look like 1/2 plus root 3 over 2 x minus pi over 6 minus 1/2 x minus pi over 6 squared over 2 minus root 3 over 2 times x minus pi over 6 cubed. Now, what happens when I take the first, second, and third derivative? Because when I take the third derivative, I should match negative root 3 over 2, but I'm not going to. Because the third derivative, or the first derivative, will bring a 3 down. The second derivative will bring that 2 down. So it's not going to match. What I'm going to have is y triple prime, and you can do this, is going to be a negative 3 times 2. And I'm going to pull that negative out of there. I'm just going to write it as 3 times 2 times root 3 over 2, and the root 3 over 2 is negative. So I actually have 6 times the third derivative of the original function. So I can correct this by dividing by 6. But rather than saying, well, gosh, I need to do this every time and correct it, notice that this is actually 3 times 2. And this is actually 2 times 1. This is actually just 1. I've got a factorial going on here. This looks like it's actually y equals 1/2 plus root 3 over 2 x minus pi over 6 minus 1/2 x minus pi over 6 squared over 2 factorial minus root 3 over 2 times x minus pi over 6 cubed over 3 factorial. And this is actually 1 factorial. And this is actually 0 factorial, because 0 factorial is defined as being equal to 1. So it looks like if I divide every term by the appropriate factorial, then I'm going to get the appropriate approximation. So just as quickly, let's jump back into Maple and see what this looks like. So I've added this last term here. I divided it by 3 factorial, and I changed this one to 2 factorial, which doesn't really change anything because 2 factorial is 2 times 1, which is just 2. And now I'm going to plot just the original function and this third degree polynomial along with the linear approximation. And you can see how now I'm starting to match more and more characteristics of this curve. So this is the exact same curve, and what I did is I just simply extended the x and y axes. So you can see that this is sine. This is my linear approximation. It does a really nice job near pi over 6, but it's horrible really fast. And this is my third degree polynomial that I'm using to estimate sine near pi over 6. And you can see near pi over 6, it really does a nice job. So if I go on and do more and more, make this polynomial more and more degrees, I should get a better and better approximation. And that is actually what's going to lead us to this whole idea of what's known as Taylor polynomials.